期中考了，来，说的下个礼拜一可以吗？有没有人那一天刚好有这个事情没办法来考试的？有没有人困难？没有。Midterm exam number 2.所以下礼拜一我们考第2次的期中考，内容呢到这个星期三上的部分没有问题。来，考完第2次期中考之后，就是要期末考了，然后就是要放假了。所以呢，大家都很愉快，第2次期中考的到来。So, any question about this midterm exam? No? Good. We have people smiling, so. Whoops. Something wrong with the display.明雄，那里有打开吗？Hey, wait a second, coming up, I think. Oh, okay, good. So last time we finished our lecture with this formula. Well, basically it tells you that if you have a motion of charges in a magnetic field, then the charge is going to feel a force. Okay, so if you send a current into a piece of wire, the current comes from the motion of the electrons. Then the electrons are going to experience a force and move this wire according to the Lorentz force equation, Q V cross B. So if you put the current loop like this, in the magnetic field, with the magnetic field, say, along this direction, then you can rotate this loop, this current loop, okay? And the torque on this current loop is expressed by M cross B. And we went through this calculation and end up having this expression. And be careful that in this expression, in addition to the magnetic field, you have M. That is defined to be the current multiplied with the surface, and the surface has a direction. Therefore, M has a direction. Very similar to the electric dipole, this M is called magnetic moment. Okay, so for dipole, electric dipole, you have Q multiplied with a vector corresponding to the separation of the two charges. And for this M, this is current and multiply with a surface. Okay, and this is a magnetic moment. In the nature world, you know, there's a in the atom. In the atom, you have some positive charge at the center, and some negative charge outside, going around with some trajectory. So this, in fact, constitute a very small magnetic moment. 所以呢，这个定义呢，跟这个 electric dipole moment 定义很类似，基本上是在描述就是自然界里头呢，很小的一个磁矩的一个物理量。Okay, so this is quite important concept, similar to this one. In a material, in a direction material, usually you have positive charge and negative charge separated by a distance of d, and we measure some effect far away from this electric dipole. Same thing in the atomic scale. If you have an atom, very often that you have a positive charge at the center, and then you have some negative charge going around, and the magnetic effect from this kind of very small atomic scale magnetic material is described by this magnetic moment. Okay, so if you put this very small magnetic moment in a magnetic field, then this magnetic moment is going to experience a torque. That magnetic field can rotate this current loop in certain direction defined by M cross B. And this equation is very general, 非常 general. 也就是说, it does not depend on the shape of this current loop. It can be circular, it can be rectangular, or it could be just random without any arbitrary shape. Okay, 所以呢，这个式子相当的这个重要，而且是 universally true for a current loop in a magnetic field. Okay, 那这个呢we're going to come back later when we talk about 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 loop in a magnetic field. Okay, now 这个部分呢，在你们 DK 圈的课本里头是在后面的部分，但是我觉得 it's useful to bring to this point because we just finished describing the magnetic force in a piece of wire carrying a current I. Okay, now let's go back to the fundamental postulate for a magnetic field. Just like electric field, we have two fundamental postulates. That is curl of E equal to 0 and divergence of D equal to the volume charge density. Well, similar to the electric field, for this B, it satisfies these two postulates. When we say postulate, it means that this is something we don't understand but observe every day in our life, in nature. Okay, so the first postulate is divergence of B equal to 0. Now, I think it's quite familiar to you that when you look at this divergence operator, then immediately you think about volume integration and then convert the volume integration into surface integration. Okay, and for the second postulate, you have curl of B equal to a universal constant called vacuum permeability multiplied with the current density. 那我们先把这个式子拿来看一下。这个式子告诉你说 well, you do a volume integration to this equation, and then use divergence theorem to convert this into a surface integration. It turns out that is equal to 0. But when you look at this divergence operator, immediately you think about flux, right? 这个 flux 是什么呢？就是一个场对一个面的一个积分。那这个所以呢think about you have some sort of magnetic field or some magnets, and then you create a surface around it and do surface flux integration. Okay, suppose that you have some field like this. So let's look at this surface integration. If my field always look like this, then this surface integration is not going to be equal to 0. If I have all the flux going out like this, right? So somehow I must have some flux going in to make this equal to 0. So to satisfy this postulate, somehow if you do a surface, if you create a surface around magnetic material, there must be some flux going out and there must be some flux going in to make this equal to 0. OK， 所以呢，你如果看这个电荷的话呢，在这里加一个这个面，在这里的话，那你可以永远都这个电场永远都是 magnetic electric flux can always go out because you have epsilon naught E and surface integration equal to the total charge inside. Okay, for electric field. But for magnetic field, this surface integration has to be equal to 0, cross-surface integration. So this means that when you create some surface, there must be some flux go out and there must be some flux go in. Okay, or let's pick up the surface like this. 你如果取一个面 like this, you always have some flux go out and some flux will go in. OK， 所以这个出去了，这个 magnetic flux 出去了，它还会再绕回来。Unlike the electric field, if this electric field just go out, it can go to infinite location. Okay, unless there's a negative charge right here, so the flux can come back to the negative charge. Otherwise, for this magnetic field, otherwise this electric field can just go out to infinite location. OK， 所以呢，这个第一个 postulate 告诉你的物理意义是什么？No magnetic flow source. Magnetic flux lines always cross upon themselves. In other words, the magnetic field line always come back to the magnetic source. 它永远都形成一个这个 loop 回来。OK， 那是第一个这个 postulate 告诉你的。所以你如果拿一个这个磁铁的话，它一定都有这个N 跟 S。但是呢 ，you can have an isolated charge. A charge only have positive sign or negative sign, but for a piece of magnet, you always have N and S, because the magnetic flux line will come back immediately. OK， 这是磁场跟电场最大的不一样的地方，在它的这个 field line 的磁场的这个 field line always come back. So there's no isolated magnetic charge. Okay, so far you cannot create isolated magnetic charge, but for electric charge you can have isolated electric charge. 那这是一个 postulate. 那磁单极呢，在科学上物理学家已经设法去找很久很久。OK， 因为磁单极的存在呢，对于有相当漂亮的这个在量子力学里头有相当漂亮的这个数学的式子的可以算出来，但是呢一直都还是找不到。那在自然界呢，就是你如果有这个 N 就有 S 的一个状况，因为这个 magnetic flux line 要回来。那when we introduce those postulates for electric field and magnetic field, it doesn't mean that there's no reason behind it. It just means that up to this point, human being cannot find the reason behind it. And certainly you are young and can always spend your effort try to explain those postulates. Okay, there could be some deep insight, some physics behind those postulates. Now you are encouraged to look into possibilities to explain it. OK， 并不是说 postulate 就是颠扑不破的，然后呢，你就是永远必须要拿它当做是这个无法解释的东西。Well, so the first postulate now give you a quite clear physical picture that the magnetic field line will always come back. Okay. How about the second postulate? The second postulate give you curl of B is equal to a proportional factor multiplying with the current density. Now, when you look at this, the curl operator, immediately now you should start to think about Stokes theorem, right? To convert a surface integration into a line integration. So 这个很自然的，现在你很清楚，你看到这个 curl operator 的话，你有一个这个 Stokes theorem 可以用。Okay, so you try to create do a surface integration for this, and then this is equal to just line integration at the boundary of the surface. And if we do this integration, then on the right hand side, because this is surface integration over the volume charge density, so you convert this volume current density into a current. 那这里头呢就有一个物理意义了。这物理意义呢就是说 ，a circulation of magnetic field is proportional to the current bounded by the circular path. 你说你今天如果说有一个路径，你做一个这个B dot dl 的 cross path integration, then this value is going to be proportional to the current crossing this surface, the total current going through this surface. Okay, and if you want to write into an equation, then you put the proportional factor to it, and this proportional factor is called vacuum permeability. Okay, equal to 4 pi times 10 to minus 7 Henry per meter, I think. Right here. Yeah, 4 pi times 10 to minus 7 Henry per meter. Henry 呢是再下来我们会介绍inductance 的一个单位，就是电导的一个单位。OK。所以这个蛮妙的，就是这个磁场呢，它会 follow 这个关系。那在人类的经验里头呢，你们都看过这种东西，来这个磁铁，它互相吸在一块。那在这个电磁学发展的过程里头，一个重要的胜利，一个重要的成就，就是把电流跟磁场这个关联在一块。因为当你拿两个这个磁铁的时候呢，把它放在一块，它们相吸。我想这个大部分人不会想到说这个跟电流有关系。OK， 那 hopefully before the end of this class, I can demonstrate some induced magnetic field from a current for you. Okay, so 在这里呢，两个重要的 postulates， 其中一个把这个磁场跟电流把它给连在一块了。And this is a major accomplishment in the science history. Okay, so now you have two very basic equations. That is, in differential form, you have divergence of B equal to 0. So when you look at this, you think about the physical meaning of it. Okay, this means that the magnetic field line always crosses upon itself, always come back. So this means that there's no isolated magnetic charges. 在你们课本里头呢，为了计算方便，有这个发明一个数学上的概念，就是 rho m. This is a volume magnetic charge. Okay, for ease of modeling the problem and for ease of calculation. But I don't want to talk about this part because this could confuse you that there could be some magnetic charges, but in fact, you don't have isolated magnetic charge. Okay, if you are interested, you just go to the textbook. 然后呢，自己读一下，但是 don't be confused with the divergence B. Divergence B tells you that there's no isolated magnetic charges. 那在你的课本里头呢，产生这个符号出来，定义这个 magnetic charge 的话，是我怕会搞混，让你们搞混，所以我不介绍。Okay. For the second equation, this is the called Ampere's law. Okay, Ampere's law relates the magnetic field to a current. So in the integral form, basically you calculate the circulation of the magnetic field to get an expression proportional to the current inside the loop you choose. OK， 所以这个呢会是你们在算磁场的时候呢最重要的这个开始的地方。OK， 有没有问题？所以 very similar to the electric field, you have two postulates. So I want to remind you that for static electric field, you have curl of E equal to 0, and then divergence of B. That is equal to, in vacuum, this is divergence of E equal to the volume charge density. Okay, and from these two expressions, you can also derive the two integral form. That is cross-path integration of E has to be equal to 0. So this is a conservative force. Okay, for this one, you have D dot ds is equal to the total charge enclosed by the surface. So you see the symmetry. You see a symmetry between the magnetic field and electric field. And don't forget that this is called electric field intensity. Okay, but this, because B is defined to be divergence of B equal to 0. So this B is sort of related to the flux. So this is called magnetic flux density. Okay, B is called magnetic flux density. Okay, because this is defined through the surface. 那我上回介绍过这个 B 的这个单位的话，在 MKSA unit 里头是叫 Tesla。OK。这个方向很重要。B 的方向跟电流的方向呢，是已经有互相约定好了。OK， 约定在哪里呢？约定在 curl of B equal to mu 0 multiplied with J. While curl operator give you a very strict definition for the direction, because curl is a calculation for the circulation of the field. Okay, and it follow the right-hand rule. Okay, so if the path, the direction of the path going, just follow the direction of your four fingers. Okay, and then your thumb, direction of your thumb is going to be along the direction of the current. Okay, 所以呢，这个along the direction of the B field， 你做一个这个 line integration。OK， 那所以呢，这里的这个电流呢是这个你选这个 path， 你 B field 的这个，对不起，我刚刚又搞混，这个 B field 的方向呢是 follow 你的这个 path 的 direction， 做这么一个 做这么一个 circulation 的一个计算。OK， 但是呢，这个方向呢，它选择的这个方向。这个 thumb 的方向基本上就是你电流的方向 ，OK， 所以呢 ，the direction for B between B and J just follow the right hand rule， 你的右手的定则 ，OK， 所以呢，我们在这里，譬如说，给一个例子，suppose you have a current flowing uniformly across this say copper wire。If you have a piece of copper wire, cylindrical copper wire, with a current flowing inside uniformly 所以 uniform 的意思就是你的 current density 在这个面呢都是一模一样的。Okay, so if you have a current flowing through this copper wire uniformly, then this means that your GA is equal, the magnitude of it is going to be equal to the total current divided by pi. The radius is b, so you have I divided by pi b squared as the magnitude of the current, right? If you want to add direction to it, then you can define, for example, moving this around z direction. And you want to calculate the magnetic field, magnetic flux density everywhere in space. OK, 那这个你的，比如说你的这个thumb 的 direction 是你的电流的方向，那你这个4个 finger 的方向就是你的 magnetic field 的方向了 according to this curve operator 的 definition. OK, 所以我们来算一下它的这个空间里头任何一个地方它的 magnetic field 的大小。OK, within this range, well, within this r less than b, so let's first pick up the region where you are less than b inside this wire. 所以呢，你取个 path。Suppose that you pick up this path with radius of r1, for example. Then, because of symmetry, 你的 B field 呢会是沿着 phi 的方向走，而且呢，它的这个大小会是一模一样。Because this is a uniform current with a uniform material. 没有问题 ，right？在这里头呢，你的 B field 呢一定是朝着 phi 的方向，因为这个 curve operator 的关系呢，你如果选择一个 path 的话呢，那 due to symmetry, you definitely select a path with a constant radius. OK, 在这个 constant radius 上头，你的 B field 会是一模一样的，因为它对称的关系。OK, so this is a very simple calculation. Just use this Ampere's law. OK. This path is going to be along some circle with radius of say r. On this plot, okay, r1, that is all right. So let's just apply Ampere's law. This is going to be the current within r. Okay, so the left hand side, your dl is equal to r d phi, and this is along phi direction. B now is also along phi direction, so you don't worry about this. At some r location and do an integration. Okay, but at the constant r, this is a constant, so you pull it out, 拿到外头来，这个 B phi is a constant value, so you just do r d phi over 0 to 2 pi, so this 2 pi r. So you get this calculation done. Now you only have to worry about the right hand side. The right hand side, according to the physical interpretation of the Ampere's law, the I is a current within the radius. Okay, so we have to calculate the total current enclosed within this path. 在这个蓝色圈圈里头包含了多少电流？我们要把它算出来。Now that we know the current density is this big, so we multiply this with the area. So on the right hand side, you're going to have impermeability, vacuum impermeability, multiply with the IR, the current inside this circle. So you have current density this big, pi b squared. This is total current. Let's put I0 on it. Everything is proportional because it's a uniform current. So you multiply a surface that is equal to the surface defined by this circle, pi r1 squared. Okay, and this is also r1 because we are looking into the the magnetic field right at R1. 所以你把这个除过来，除到这边来，除到这边来 ，2 pi R1, then you get the answer. Okay, so this is a very simple algebra that you can calculate for you can do for to derive the magnetic field inside this wire. For outside this wire, the calculation is even easier because now, say you have a wire like this, and then you want to get the magnetic field at, say, R outside, and the total enclosed current is going to be the total current. So on the left hand side, you have the same thing, B phi multiplied with 2 pi R, and then on the right hand side, you simply have the total current. Okay, and then you end up having the B phi equal to mu naught multiplied with I naught divided by 2 pi R, and the direction is along phi direction. OK， 有没有问题？所以呢，这个下一个问题就是 R 大于 B 的时候呢，这个 B phi 就是这么大。And this I is the total current. OK， 所以这是第一个例子，你用 Ampere's law 下去算它的这个电场跟电流的关系。那这些这个计算呢，你就是花一个力气下去练习一下，应该就是没有问题。但是方向上头的话呢，用你的右手来定义，因为这个 B field 呢，这个 circulation 的这个方向呢，你必须用你的右手定则下去做确定。Okay, so this is sort of just some effort you have to spend, some practice you have to do to get yourself familiar with using the Ampere's law. 那在这里头呢，你看到你如果把它跟以前我们算电场状况一样 ，you plot the magnetic field versus R, okay, and so the magnetic field inside this wire is going to increase with the distance because if you move in this direction, your current enclosed inside this circle, inside this area is going to be to increase as well. OK， 所以呢，这里头包含电流呢越来越大，所以你的这个磁场就越来越大。但是呢，超过这个地方at the radius, then your magnetic field starts to drop. Okay, because all your current is going to enclose within this area, but now you don't have current outside. So with a constant current, the B field drop with radius, depending on 1 over R, OK， 所以这是 B phi versus R 的一个图，在那个地方。Well, we can also wrap the wire differently. For example, this is a so-called toroid. OK， 这是一个 toroid. 然后呢 you can just wrap the wire around some, say, some tube. And then if I cut this, if I have a toroid like this and I cut it, then you're going to see this geometry. Okay, so you have wire wrapping around sort of a tube, but this tube going around a circle. 所以在这种状况之下呢，你的 magnetic field 会长什么样子？ Well, if you have a single wire like this, your magnetic field is going to go like this, right? So now you have a wire going around like this. You can add the magnetic field together right at the center. 你可以想见，在这正中央的地方呢，你的任何一点呢，你产生的磁场呢，都是 follow 你的右手定则。所以呢，你如果是绕的这个圆圈 ，and then use your finger, you're going to see that right at the center, the magnetic field is going to go along z direction. Okay. the magnetic field if you go around a loop, okay, if I have a current like this, 那你的这个磁场呢，就是say going out like this, and then go in like this, okay. 但是呢，你如果把这个变形变成这个样子的话，那让你的电流这样子走的话，那在正中央的地方一样，在任何一点你还是用你的这个右手 try to find out the direction of your magnetic field. Then,你的这个4个这个在正中央的地方，你会发现它的这个磁场呢是 go into this ball right at the center. Okay, just point your thumb along the direction of your current. Okay, and then at any point right at the center, you're going to have the magnetic field go inside. So in other words, if you have a current going around a loop, then you can simply use your forefinger around the direction of your current to determine the direction of your magnetic field. Okay, 所以呢，这4个 finger 的方向呢，可以是这个磁场的方向或者是电流的方向，然后呢，你的这个 thumb 的方向呢，就是你另外一个物理量的方向。OK， 在这个例子里头呢，我是把这个拇指朝着电流的方向来决定我的这个 magnetic field 的方向。在这个例子里头呢，我是把这个4个手指的方向呢朝向电流的方向来决定我的磁场的方向。OK， either way you can determine the either I or B。那你的这个4个这个finger 的方向永远都是绕着一个圈圈。OK， so for this case, you can easily determine that your magnetic field is around phi direction. OK， 因为在这个例子里头呢，譬如说你把4个这个 finger 的方向 just follow the direction of the current, then you can determine the direction of your magnetic field along phi direction. And be careful that 在这个里头呢，这个电流呢是进到这个 ball 里头去 ，so you see cross on each wire right here, and then the current going out from this ball, you see a dot in the inner radius. OK， 所以呢，你如果是follow 这个电流，譬如说 if I pick up this point and then use my forefinger to follow the direction of the current, then the thumb direction is going to be along this direction, 这个切线方向。OK， 所以呢，这个箭头是朝这个方向。So for magnetic field direction with respect to the current, you have to sort of follow the you have to use the right hand a lot. Okay, good. Now, because of symmetry, you know that the magnetic field is along this phi direction. So the calculation you have to do is that pick up the Ampere's law, okay, and then do a cross path integration along this path, okay. 那 dl 呢就是这个方向，那这个圆周呢就是在这个圆周上头有 b is a constant. 所以once you have the b is a constant, then you can pull out this b from this integration. Okay, so this calculation becomes very simple. B is a constant, so you have b at a certain r multiplied with this dl cross path integration. Basically, it's just 2 pi r. Okay, because it's a circle right here. 它是一个圆。On the right hand side, that is going to be equal to a permeability multiplied with the total current. Well, inside this loop, you have many currents. 每一个这个点呢，就是有一个电流的冒出来。假设你有 n 个点，每个点有一个电流叫做 I 的话，因为你是从这里提供一个电流进来，然后绕，然后再绕出来。So on the right hand side, you have mu0 and I. So you end up having BR that is along phi direction equal to mu naught I and I divided by 2 pi R and then along phi direction. This is the answer for your B field. Okay. So this is called toroid field. 那我希望下回我能够拿一个 toroid 来让你看 ，OK？ 去年我买了几个，但是去年那几个不晓得在哪里，我还得去找找看。所以这个计算有没有问题？这个 toroid 没有问题的话呢，就是我如果把这个 toroid 呢，这个半径变得很大，非常大。那这个 r 趋近这个无限大的话，那基本上呢，你会看到一个这个任何一个这个区域呢，你看起来就像个直线一样。Okay, so let's try this. If I have r approaching infinite, then this n also approaching infinite. So my b phi now is going to approach mu naught divided by multiply with I and divided by n 2 pi r. But r approaching infinite. At the same time, n also approaching infinite. Right? 所以这个值会 convert to a value called n. This n is the number of wires per unit length. 那这个如果把一段切下来的话呢，你如果看一小段的话呢，那你会有一个 b 的场，类似这个样子。那因为 r 很大，所以 almost a straight line。这个东西叫做 solenoid。Okay. The configuration is going to look like this. 这个 configuration 会变成类似这么一个样子。If you just cut a small section, allow r approaching infinite. Okay. 那我们刚刚还少讲了一个部分，这个部分是什么？在这个里头跟在这个外头 ，basically you don't have magnetic field because if you choose a cross path for r less than this value, okay, for r less than b minus a, then you don't enclose any current in this path. Therefore, within this region, you don't have magnetic field. And if you choose a radius of this big, whatever current coming out is equal to whatever current going in, because 你如果有一个电流从这里出来的话，就有一个电流从这里进去，so the total current enclosed by this surface is going to be equal to 0. So in this region and in this region, basically you don't have magnetic field. Because the Ampere's law tells you that you have to calculate the total current enclosed by this circular loop. Okay, you choose for this for a particular problem. 没问题，没有问题 ，right？ 所以呢，这是叫做 toroid， 是电子电路里头其实蛮常见的一个元件。当你做这个inductance 的时候，经常会有这么一个绕法，因为这个绕法呢，可以把我们的这个磁场呢局限在一个小范围之内。 那这里头跟外头都没有。Okay, any question? Then for solenoid, if you allow your construction for this wire wrapping to be just a straight line, then the configuration look like this. Okay, and assume that you don't worry about any fringe field coming out or going in. But with this configuration, think about this. If you have a current like this, you have a magnetic field going into the ball. 所以呢，你可以用你的这个4个手指头 just follow the direction of the current to determine the direction of the magnetic field. And 在这里呢 we assume that this length is very long. So the magnetic field, when you come back from outside, the magnetic field is very weak in this region. 假设这个的长度很长很长 ，OK， 所以呢，这里这个 magnetic field 回来的时候呢，经过很长的距离之后，这里的区域的这个 magnetic field 很弱 ，so you only have to, if you pick up the Ampere's law, again, you pick up a circular a path. Okay, you pick up a path, and the magnetic field outside is very weak. So you only have to calculate the magnetic field in this region. But because of symmetry, 在这个方向上头，在这个方向上头 you don't have magnetic field either. Okay, because you have a circular loop like this. And then so all the magnetic field is concentrated along the axial direction. 那所以呢 when you do this calculation, you only have to calculate the path integration for the B field inside the solenoid along the axial direction. And on the right hand side, if you have N current in this region, then you have Ni multiplied with mu zero. OK， 所以呢，你在整个计算里头，其实就是把这个 Bz 乘上你的这个长度 L， and on the right hand side, this is mu I multiplied with this N。但这个 N 呢，在这里呢，你可以把它写成每单位长度里头有多少个电流乘上你的长度。Okay, so this is sort of the number of wires per unit length in the solenoid. Okay, so with this, you cancel out this L and this L, then you end up having a Bz equal to the vacuum permeability multiplied with the current, and then multiplied with the density of the wire, the axial density of the wire in your problem. 那在这里头呢，你不要忘了，就是当你计算这个过程里头，你有一些这个 assumption， 就是这个长度要很长很长，这外头的长呢必须是接近0 ，otherwise you are not going to get this magnetic field. So very often when you do one experiment, when you do a real experiment, your Bz field in fact is could be quite significantly smaller than this value. 可以比这个值呢小很多。That is because that your solenoid is very short, and you have rather leakage field outside this region. Okay, you have leakage field to go outside. Therefore, you don't get this full magnetic field predicted by this expression. 所以你在做实验的时候要留意一下，就是你这要够长、够接近中心的时候呢，你的场才会接近这个值。OK， 那这个东西叫做 solenoid。And as I just brought out to you that in fact you can calculate, you can derive this expression by allowing the radius of this toroid to be infinite. Okay, so 我刚刚已经把这个式子写给你了。你如果把这个 r 这个 toroid 的这个 r 呢取无限大的时候呢，这个 n over 2 pi n is going to reduce to the number of wire per unit length. Okay, if you do so, you end up having an expression. 你的这个式子呢，这个 b phi 很自然的，你就是得到 mu naught I n 这个 solenoid 的这个式子出来。 when R approach infinite。OK， 所以这个是toroid 跟这个 solenoid 的计算。那你以后再学的话，这个计算都相当的容易，因为你有一个这个 B field 呢是一个 constant， 你可以把它拉到外头来。Just like the way you use Gauss law, your electric field is a constant on the Gaussian surface. OK， 所以等一下10分钟之后我们再继续上。